Subspace. In topology first, we start unit third. That is, first definition is subspace. If x tau is the topology, and here if x tau is topological space and A is subset of X, then tau dash, that is equal to tau dash is G intersection A such that G belongs to tau, that is G is here element in the tau. Then this tau dash is a topology on A, topology for A. Then A is called subspace of X. Okay, this is definition of subspace. Now example, let here X equal to ABC and tau equal to topology on X, that is suppose phi singleton set A, singleton set B, 2 point set AB and X. This is topology on X, and here we take A equal to set of points, 2 points AB, which is subset of X, and here we take tau dash equal to here, that is we know for subspace A tau dash is G intersection A such that G belongs to tau, that is here for every element of this tau, this is G, say it is G1, G2, singleton set B is G3, 2 point set AB is G4 and X is G5. And for tau dash, here we have to find, for tau dash we have to find, that is intersection of this G, that is phi intersection A, singleton set A intersection A, that is tau dash is equal to here phi intersection A, singleton set A intersection A, singleton set B intersection A, 2 point set AB intersection A and X intersection A. Now here we get tau dash equal to, that is phi intersection A is phi, singleton set A intersection A is nothing but 2 point set AB, therefore A intersection AB common point is only singleton set A. Again B intersection A, here B intersection AB, that is common point is B. AB intersection A, that is AB intersection AB is again 2 point set AB, and X intersection A is here A, and we know this tau dash is topology for A, that is phi and A belongs to this A, tau dash. Again here union of such a sets is again belongs to tau dash, intersection of sets belongs to tau dash is again belongs to tau dash, and therefore tau dash is topology for A, and therefore A is called subspace of X. Now we know here discrete space, discrete topological space, discrete topological space for, that is for any set non-empty set X. Here tau is equal to power set of X, then this tau is called discrete topology and X is called discrete topological space. And again we know definition of trivial topological space. Here if x equal to x is not equal to phi, that is x is any set more than 1 points with 1 points, then here if tau equal to topology tau equal to set of only phi and x, then this tau is called trivial topology and x is called trivial topological space. Okay, and space of discrete topological space is discrete. That is here if tau is, that is a is, sorry, here x is any set and a is subset of x is discrete topological space, x is discrete space, and here a is subspace of x, then his a is also discrete topological space. Okay, now next result is if x is trivial topological space and a is subset of this x, then a is also trivial space. That is next result is here, that is subspace of trivial space is trivial. Okay, there are two results. First result is, that is on discrete space, that is any subspace of discrete space is discrete, and second result is any subspace of trivial space is trivial. Now next result is, that is if there is x is here topological space and a1 is subset of x, and here a2 is subset of a1 and a1 is subset of x. If a1 is subspace of x, if a1 is subspace, then here a1 is subspace, therefore here subspace of, that is a2 is subset of a1 and a2 is subspace of a1, a2 is, this a1 is subspace of x, a2 is subspace of a1, then we can write here a2 is subspace of x. That is next result is a subspace of subspace is subspace. What is result? A subspace of subspace is subspace. That is here if we see again this result, that is here given, that is x is topological space, then a1 is subspace of x and a2 is subspace of a1, then here we can write, then we can write a2 is subset of a1 and this is subset of x. That is here a2 is subspace of a1, a1 is subspace of x, then a2 is subspace of x. That is subspace of subspace is subspace. Okay, let this. Now we have to see next result, that is we know here a is subspace of x, a is subspace of x, that is here for tau is topology for x and tau dash is topology for a. That is, see this element of tau dash we can written as g intersection a such that a belongs to, sorry, g belongs to tau. Now here, that is for subspace a, open sets in this subspace is nothing but g intersection a. That is open sets in subspace A is of the form G intersection A. Okay, that is, here we, if we take that is open set in A, that is it is of the form G intersection A. If here we write here closed sets of A, that is we can write here again G intersection A. We take neighborhoods of X, then we can write neighborhoods of A again of the form G intersection A. And we take base in X, similarly we can take base in A as G intersection A. For by using this result, that is elements of A are in the form G intersection A, we take one theorem, that is, see, statement of this theorem is, if A is subspace of topological space X, then first result is, that is H is subset of A. This H is open in A if and only if H is of the form G intersection A, where G is open in X. Second result is, here F subset of A is closed in A if and only if this F equal to K intersection A, where K is closed in X. What is result? F subset of A, that is set in A, is closed. That is F subset of A is closed if and only if. We can write here F as K intersection A, where K is closed in X. Next result is, that is for closure. If E is subset of A, then closure of E over A is nothing but A intersection closure of E over X. What is result? See again, if E is subset of A, then closure of E over A is nothing but A intersection closure of E over X. Now next result for neighborhood. If X belongs to A, then V is neighborhood of X in A. V is neighborhood of X in A if and only if V equal to U intersection A, where U is neighborhood of X in X. Okay. Now next result is, E is subset of A, then for closure we get again same result. For neighborhood again we get same result. For neighborhood base again we get same result, and for base we get same result. Okay. Now next result is, that is interior of E over A contains A intersection interior of E over X. That is relation between A and X is, here A is subset of X. That is interior of E over A contains A intersection interior of E over X. How? Let's see. Okay. Here let X be plane with usual topology. That is, here X equal to R2. Now A equal to E, that is, suppose this is X axis, that is A is subset of this X, that is from this R2 we take only X axis, that is E is subset of this X, and interior of E over A equal to A. We know interior of this X axis is again X axis, while interior of E over X, that is interior of E on this plane, is nothing but phi, and we know that is this phi is subset of A. Therefore we can write here interior of E contains A intersection interior of E. Okay, we get first result. Now we take same example for frontier, that is frontier means boundary, that is E is here subset of x, plane x, and here e equal to a, then frontier of e over a is equal to phi, and frontier of e over x equal to a. We know this result. We saw example on this frontier, and therefore we can write here one more result, that is frontier of e over a is subset of a intersection frontier of e over x. Okay. Now for definition of continuous function. Okay, definition of continuous function. If we take two topological spaces x and y, here f from, there is function f from x to y. Okay, and if that is this function f is continuous, it is possible only if there are two sets x and y, and there is function f from x to y. If we take one point x naught in x, then we get here image of this x naught is f of x naught. Okay, if we take here neighborhood of x naught, suppose this is v is neighborhood of f of x naught in y, then there is neighborhood of x naught, this is suppose u in x, there is neighborhood u of x naught in x, such that we know this f of u is subset of this v, image of this u is subset of this v. That is, this function is continuous. That is, we can say that function f is continuous on x if and only if f is continuous at each x naught belongs to x. We see that is definition of continuous function. Let x and y be two topological spaces, and let f from x to y, then f is continuous at x naught belongs to x if and only if each neighborhood v of x naught in y, there is neighborhood u of x naught in x, such that f of u is subset of v. That is, we say that f is continuous on x if and only if f is continuous at x naught belongs to x. Okay. Now next theorem, that is here again, if x and y are two topological spaces and here function f from x to y, then following conditions are equivalent. There are four conditions which are equivalent. Four conditions: a, b, c and d. First condition is a, that is f is continuous. F is continuous. Second, here, that is if we take here h in y, which is open, then here f inverse of h is open in x. Okay. Next condition is, that is if we take k is closed in y, then f inverse k is closed in x. Okay. This is third condition. Fourth condition is, that is if e is subset of, for each e subset of x, here f of closure of e over x is subset of closure of f of e over y. Okay, these four conditions are here equivalent. Let us see result. Okay, that is, theorem is here, if x and y are topological spaces and f from x to y function, then the following conditions are equivalent. That is, first condition is f is continuous. Second is for each open set H in Y, f inverse H is open in X. Third condition, for each closed set K in Y, f inverse K is closed in X. And fourth condition, for each E subset of X, f of closure of E over Y is subset of f of closure of E over X is subset of closure of f of E over Y. Okay. Now next result is a composition. Next result is on composition. That is, there are three topological spaces x, y, z. If x, y, z are topological spaces, and here function f from x to y and g function from y to z are here continuous, then composition of this f and g, that is equal to GOF from x to z is also continuous. This is theorem on composition. Okay, let us see this result. That is, if x, y, z are topological spaces and f from x to y and g from y to z are continuous functions, then their composition GOF from x to z is also continuous. Now next definition is restriction function. That is, here if function f from x to y and if a is subset of x, then f restricted to a from a to y, a into y, this is restriction function defined by, that is, f restricted to a of a equal to f of a for each a belongs to a. This is the definition of restriction function. That is, for function f from x to y, here we take subset a of x, then f restricted to a from a to y defined by f restricted to a of a, that is, here we take point a belongs to a, f restricted to a of a equal to f of a for all a belongs to a. Let us see definition. That is, here if function f from x to y and a is subset of x, then we use f restricted to a denote map from a into y defined by f restricted to a of a equal to f of a for each a belongs to a. Okay. Now next theorem is here, that is, if a is subset of x and f from x to y is continuous, then restriction function is also continuous. Let us see result. That is, here theorem is, here if a is subset of x and f from x to y is continuous, then restriction function f restricted to a from a into y is continuous. Okay. Now next result is on two restriction functions. That is, suppose there are two sets a and b. Here there is function f restricted to a and f restricted to b. That is, here a and b are subsets of x, and here for these two restricted function, if these two restricted functions are continuous, then function, that is, f from x to y is also continuous. Okay, so let us see result. That is, here if x equal to a union b, where a and b are both open or closed in x, if f from x to y is any function such that both f restricted to a and f restricted to b are continuous, then f is continuous. Now next result is, that is, if we take function f from x to y. Okay, we take function f from x to y, and if here y is subset of z, that is, here function f from x to y is continuous if and only if f from x to z is continuous. That is, f from x to y is continuous if and only if f from x to z is continuous, or f from x to z is continuous if and only if f from x to y is continuous. Let us see result. That is, here suppose y is subset of z and f from x to y, then f is continuous as a map from x to y if and only if it is continuous as a map from x to z. Okay, now we take next definition of homomorphism. Definition of homomorphism. Here, for this definition, there suppose there are two topological spaces x and y. If x and y are two topological spaces, and function f from x to y is said to be homomorphism, that is, if f is 1 1, f is onto, f is continuous, and also fourth condition is, that is, f inverse is also continuous. Then by using these four conditions, then f is homomorphism. Okay, and if f is everything but onto, then it is called embedding. Okay, let's see definitions. That is, here if x and y are two topological spaces, a function f from x to y is homomorphism if and only if f is 1 1, f is onto, f is continuous, and f inverse is also continuous. This is definition of homomorphism. And here x and y are homomorphic. We say in another way, x and y are homomorphic. Next definition is for embedding. If f is everything but onto, then we call it is embedding from x to y. And now next is, we say that x is embedded in y by f, that is, x is embedded in y if of f by f if and only if f is homomorphism between x and some subspace of y. Okay, now next result is, that is, if we take two functions, that is f from x to y, homomorphic function, another function is g from y to x is another homomorphic function on same set, then but direction is opposite, then composition of this f and g or g and f, that is FOG or GOF, these are identity maps. These are identity maps. Let us see result. That is, a continuous map from f from x to y is homomorphism if and only if there is continuous map from g from ay to x such that composition GOF and FOG are identity map on x and y respectively. Now next result is on these two topological spaces, that is, if x and y are topological spaces and there is function f from x to y. Suppose this is 1 1 on 2, then following conditions are equivalent. First condition is, that is, f is homomorphism. Second, here g subset of x, here if g is subset of x, and then f of g is open in y. F of g is open in y if and only if g is open in x. G is open in x. Next, Third condition is here f subset of x, and then here f of f is closed in y if and only if f is closed in x. And last, fourth condition is that is e subset of x, then here f of closure of e over x is subset of closure of f of e over y. Okay, let's see result. That is here if x and y are two topological spaces and f from x to y is 1 1 and on 2, then following conditions are equivalent. First condition is f is homomorphism. Second is if G is subset of x, then f of G is open in y if and only if G is open in x. Third condition, if f subset of x, then f of f is closed in y if and only if f is closed in x. And last is if E is subset of x, then f of closure of E over x is equal to, here equal to, result is equal to closure of f of E over y. Okay, now if we denote x homomorphic to y by this, x homomorphic to y by this symbol, then the relationship that is homomorphic has the following properties. That is, first property reflexive, x is homomorphic to x. Second property, that is symmetric property, if x homomorphic to y, then y homomorphic to x. And third is, that is transitive homomorphic, that is here if x homomorphic to y and y homomorphic to z, then x homomorphic to z. Okay, thank you.